NVIDIA's Chief Data Center Architect. Coming up, we've got Wade Vinson coming to the stage.
All right. Well, Kirk's a hard act to follow, so I'm going to try to educate and inspire you folks. And so, we're going to be talking about how everybody can transform data centers into AI factories. We're going to be talking about the why it needs to happen, what we're doing about it, how we're doing it, and the who is all of you folks who can participate and accelerate it. So the first piece of bad news is you didn't get Jensen Huang, at the conference. And so, I'm second. I'm not going to wear a leather jacket or anything. Jensen is a computer scientist. I'm not. So he spoke at Computex in Taiwan in June, and I thought he had a lot of cool chalkboards that describe the why that as a mechanical engineer, as a data center person, I'm not really good at that, but I'm going to steal a few of them from him here. And then I don't get in trouble because they're his slides. So why is this transformation happening? And it comes down to one key fact, and that is since CPUs were invented in the 1960s, they have started to flatten off in performance. Gone are the days where you could replace 4-year-old, 8-year-old GPUs with the next technology and move up the slope. And that's what's been happening for multiple generations. The CPU always got better. But basically, the lack of Moore's law, Dennard's scaling has prevented the increase in performance for CPUs. And when I talk about CPUs in this data center, I'm just using the term like a traditional colo, hyperscale, 15 kilowatt data center. What's wrong with that? What's wrong with that is even pre-COVID, the data demand is incredible. And it doesn't take a business degree person to figure out that we cannot have a gap between the white line and the blue line, because what happens is we have to meet the white line. And so I would argue the blue hashes I've added, those represent these multi-hundred megawatt data centers you're hearing about, these gigawatt data centers, because they're having to compound the flat part of the curve, the inefficient part of the curve. The only way to meet the white line is to just put more of them in, as inefficient as they are. Jensen's been calling that computation inflation, and it's that compounded inefficiency that is just not sustainable. But the cool thing is, I had actually a GeForce shirt on yesterday showing the GPU for a video for a workstation. But the GPUs hit the data center market about 2012, and we've continued to grow, we've continued to innovate, and it's keeping up with the white line. And again, for the business folks in the room, the retained waste that we're capturing with GPU computing, accelerated computing, versus if you were doing it with CPUs, just 23 through 25 is over $1 trillion. And we're just scratching the surface of that. So this is, the why it's happening. And so a lot of it is based on large language models, training, a handful of companies doing that. But what we see from this is that every application that is processing intensive should be accelerated. So again, a little more of that, why that's the case. So if you think of a typical computing application, a processing intensive application, the CPU's the traffic cop, it manages the IO traffic, it manages the memory traffic, CPU to CPU. But then a lot of the processing intensive work wants to be done in the CPU core. Well, there's just not all those resources in it. And so you have to stack up those workloads, those parallel processes, because you can't, that ended up being in serial because you only had so much resources. And so it takes 100 units of time, whether that time is a couple seconds, minutes, hours, or in the case of large language models, weeks or even months. And so what we decided to do was to combine a CPU and a GPU together. And by doing that, all of that work that wanted to be parallel can now be parallel. So literally, there are many applications that take 1 unit of time versus 100 units of time. Now, surprisingly enough, that doesn't come for free. It does take about 3 times more power to get that 100x speed up, and it's about 1.5 times the cost. For those people who are involved in data centers, think about it. You've got a $400 million data center of CPUs, you add $200 million of GPUs, and voila, you get the 100x speed up. Apply that math. Look at that. That is not a small increase. That is not a multiplier. You're talking about a 30 times performance per watt if you get that 100x speed up, and a 60 times performance per dollar. So we don't talk about other metrics, that don't make sense, but these are the real business metrics here, the real watts metrics. As Jensen likes to say, the more you buy, the more you save. Because every time you're not buying a GPU, you're leaving money on the table. And by the way, he didn't just start saying that. Matter of fact, there's a YouTube video back in 2008. It wasn't even called GTC, it was called Envision. It was the first conference, and Jensen decided to bring the greatest engineers of our time up on stage to demonstrate accelerated computing. And of course, that's Adam and Jamie, the Mythbusters. So they got up there and they showed what it would take to do like a CPU to paint a smiley face. And then they gave an example of accelerated computing. In 1 second of time, they painted a much more famous, a more detailed smiley face. So for anybody who doesn't know a lot about NVIDIA, I send this to my family and friends when they ask what I do, and I'm like, that video is still out there. It's funny, it's entertaining, and it's still true today. Now, we haven't been sitting still since 2008 or 2012, and so this is the what? What are we doing about it? Well, we're continuing to innovate. And so if you look at the improvements in large language model training. So this is, I'm using the ChatGPT-4 that I don't even go back to Pascal. But at HPE, I was building systems for some of the people building large language models. And just look at the improvements from Ampere to Blackwell. 40 gigawatt hours, that's a lot, down to 3 gigawatt hours to train the model. But people are going, in this room are going, well, I don't really play in that space, right? I'm not a large model builder. There's only a handful of them. Well, guess what? There's probably about once a week 2 new large language model and large model builders. And we're just in the infancy. So there's going to be a lot more large models that the energy efficiency required to train the model is still very important. But everybody says, hey, where the money's made, inference, right? I want to know the energy efficiency metric for that. So again, ignoring Pascal because it was so long ago, if you just look from the A100 Ampere to Blackwell, 0.4 joules per token. Remember I said I was going to educate you a little bit? What's a joule? What's a token? I'm a data center guy. I know watts, BTUs. So at 0.4 joules per token, let me give you an example of what that means. So if you go on to a ChatGPT session and you talk for a while back and forth with it and you get the perfect answer you want, this isn't just you even see it now when you Google something, it's automatic, that an average answer is about 3,500 tokens. And so that's 1,400 joules. Somebody made me put the math down to prove that it was right, that it's 0.4 watts per hour. That's nothing, 0.4 watts per hour. People talk about water bottles. How many water bottles does it take? I argue that's like a one study of a Microsoft data center of water usage from GPUs a couple years ago. But what is 0.4 watts an hour? How little is that? So I had to go Google it, or actually went to Amazon and said, what's 0.4 watts? And that little LED light bulb by the side of your bed, and you don't even spend the money to have it turn off in the daytime because it's so energy efficient, you don't care. You could fill this whole stadium. You could fill the Louisiana Superdome with these light bulbs and you wouldn't worry about it. You'd put it everywhere, you wouldn't care. Quite frankly, what I would care about is, why are there pitchers of water sitting next to my bed? My dogs would knock that over in a heartbeat. I'm not worried about the power of it. And so it's going everywhere. So what does everywhere mean? Who would have thought that, everybody kind of thinks about accelerated computing for certain things, large language models, but there's over 500 million CUDA-enabled GPUs. We've got over 5 million developers. So this is a virtuous cycle. And nobody would have thought that telco, the most pedestrian, you got to be certain ways, could benefit going from x86 to accelerated computing on aerial RAN. No one had thought that a SQL database query and processing would benefit from it. So it's happening everywhere. I'll encourage you to go look up accelerated computing, energy efficiency, and CUDA. We just did Hot Chips as a big conference white paper, and we wrote a white paper, and I think we showed over 100 applications that are accelerated. Some of them 20x, 30x, 80x, 100x, 180 times. So those numbers I showed, the benefits from it, it's now not just large language models. It's not just generative AI. It's everywhere. So how are we doing it? And the answer is we continue to innovate. So Jensen showed the world a 6-year roadmap in June. How many other CEOs go out there and say, hey, you can buy today, you can buy tomorrow, you can buy the next day. The sooner you buy, the more you make money. Don't wait for the next TikTok because you don't know when it's coming. So we're innovating across the whole platform. It's the GPU, it's the CPU, it's the NVLink fabric, it's the interconnect that brings them all together, whether it's Ethernet or InfiniBand. And every year, we're going to be coming out with the latest and greatest to continue this acceleration, this efficiency. Now, you're saying, okay, how does that affect me? I'm a data center guy or girl, and so this just looks like a collection of chips, in a system. Well, it's all been about building out a cluster, a supercomputer at scale. And in the big white box in the bottom, when we first came out with the first GPU that was bigger, we put it into a pod. We told the world about it in 2019 at 16 racks. The number 5 supercomputer in the world when A100 came out. And then, of course, unless you've been sleeping for 3 years, you probably know about ChatGPT, and you look at collections of pods for H100s. And so we intentionally, with many people in this room, hopefully everybody's participating in this great thing that's happening, we intentionally try to make it work in a standard data center. Low density, air cooling, spread it out, put the network in the middle. But a funny thing happened, and that is customers would start coming back to us and they're saying, hey, I'm going to have better hot aisle containment. I'm going to put rear door heat exchangers on it. I'm going to do better fan walls, and I'm going to make it a lot smaller. And so that into the SuperPod that we came out with in 2023, density for density's sake is dumb. We didn't make it smaller because we could. We made it smaller to get the performance and performance per watt and performance per dollar of staying in a copper interconnect as opposed to going to an optical interconnect. Optical's great for long distance, but for short distance, it doesn't fill the bill. It doesn't fill the bill for 4 reasons. Number one, you ever play with an optical fiber? You ever break an optical fiber? You ever have to write so it's a little bit finicky to route. You have to take some special precautions. Okay, I can get over that. It's actually, optics is got a loss on performance because still today, the native signal is electrical. So a laser encodes it to optical, then on the other side, the laser decodes it, and so that's a slight performance decrease. I told you there are 4 things. Those are 2. Those aren't the big 2. The big 2 are, did I say it was a laser? Do you think a laser uses some power? 17 watts at the current speed per transceiver on both ends. So we're talking about each one of these racks, 20 kilowatts a rack more to go into lasers. And I bet you figured out that lasers aren't free either. The average cost of a copper port versus an optical port is 7 times less for copper instead of optical. So those are the reasons that are driving this density, not for density's sake. So that's the big lesson to learn, is that we're going to continue to push this. And you don't have to believe me. You can look at what some of our partners are doing. So HPE, Dell, Lenovo, and Supermicro. And so they put liquid cooling, did 8 chassis a rack, collapsed 256 GPUs into a 5-rack footprint, so much so that Elon invited the CEO from Supermicro to take pictures in his giant data center. And his other partner, our other partner, not to be outdone, Michael Dell, said, hey, wait a minute. I want to show my stuff. So we're in Austin. So go find your Dell buddy and go visit this factory where they're putting all this together for Elon. And so other people are continuing to push on that density to have better copper, better performance. That's all backwards looking. So let's go to the future. So hopefully many of you folks have seen our SuperPod today. And this should look familiar to you as a data center. Oh, I recognize a CDU. There's water under the floor. Water could be overhead. We don't really care. It's not into every rack. Notice there's only liquid into some of the racks. And there's some racks that are kind of more pedestrian. And so Jensen on stage at Computex, he walks over to the side and picks up the giant copper thing and puts it down. So there are 4 of those in the back of each rack. But that is what makes 72 GPUs live as one. All of the H100 stuff you see there's 8 GPUs there with the NVLink switches. Am I pointing to the right thing? And so this is like 72. So that's all in copper, and then we connect them together at high speed. And so the number one rule now for the data center, the number one takeaway is you see water, right? Yeah, you can convert liquid to air, but the reality is, data centers really want to be water. And so let me give you some numbers. I've been hearing people say, and I've asked here, what do you think the water temperature needs to be to do direct liquid cooling? I've heard something 25, 28, 30. Our chips run at 85 and 90 C. That means that I need 45 C water into it. And most CDUs, a 4C approach temperature, can make 41 C. What does that mean? That means it's a dry cooler everywhere in the world. So I don't need makeup water, I don't need compressors, I don't need all of that stuff associated with it. And because I'm returning 65, quite frankly, for the 5th industrial revolution or 6th industrial revolution, we need to use that water. That it's just ridiculous that we power in and we pay money to remove the heat. We got to use that heat. But at the same time, there's some equipment that's got copper in it as well. That's standard equipment at the end of the row. Now, I could run that equipment at 35 or 40, but carbon-based life forms, us, like it a little bit chillier, and they live in the data center, and there's storage racks and network racks and many other things in the data center. So really, you got 2 water feeds. And people are saying, well, the water feeds are close enough. I want to use 1 water feed. And I'm like, please go do the math. Please go do the analysis of the savings that you get, efficiency costs by having 2 water feeds. So the other thing people hear about is, oh yeah, I heard this rack is so high power. How are we going to do it? But remember, as you look at this cluster, not all the racks are the same. So the racks that have the water in them, are 130 kilowatts today with liquid cooling in them. But the racks around them, the standard support racks, are just 14 kilowatts a rack on average. And a lot of people put them in 800 millimeter wide racks because they're cabling. So your average power density for a SuperPod is only 62 kilowatts a rack. But that's not nearly as scary than somebody telling you X watts in a rack. Everybody who runs a data center built a data center, designed a data center that had a 20 kilowatt a rack, a 30 kilowatt a rack. I hope everybody in this room would say, drop the mic, we're done, 62 kilowatts a rack, that's easy. We know how to go do that. So this collection right here, this is showing 576 GPUs. It's about 1.1 megawatts today, and it's that collection of NVLink, copper connection, high-speed Ethernet or InfiniBand that is driving the 30x performance, the 30x improvement in performance per watt, and the 60x increase in performance per dollar to get rid of computation inflation. So I submit to you, what if in the future, in our next 5 generations of computing, that in order to continue to drive this innovation, that power went up? What if local power went up to keep this copper domain in? What would the data center do? So I'm going to make a prediction. You guys ready? I predict that local power will go up to double in 2018. Wait, did you mean 2028? No, 2018. Wait, that's in the past. How can you make a prediction about it? Guess what? In 2018, Cray designed the Shasta system. Anybody in this room a Shasta designer? Where's Mark? I know he's got to be here. There's people in this room who designed this system. We thought we were crazy designing a 400 kilowatt rack. It was 300 at the time, it's now 400. And we looked at today and gone, dang it, I wish I would have put bigger rectifiers in it. Dang it, I wish I would have put 2 water feeds in it. There's Jensen with Antonio Neri standing in front of Los Alamos National Labs. So that cluster they're standing in front of and the one above it, That's 3.2 megawatts. So think about 8 racks at 400 kilowatts a rack. So it's already been done. And by the way, you can see them moving in with special carts. Tens of thousands of racks have been shipped in Europe, Asia, freight elevators, raised floor, over threshold. So the industry knows how to do it and been doing it for a while. But many of you don't get to go build a custom Department of Energy data center. You have a standard data center. You have a commodity-based data center to be cheap, efficient, fast, and scale. What could be more commodity than the open compute rack? Rob Coyle here today? Yeah. What could be more simple than that? And so these are photos from GTC. So you know there are 8 power shelves in a rack today. They've gone up from a 30 amp connector to a 60 amp connector. The next logical step is a 100 amp connector. So what that means is commodity computing is already 460 kilowatts a rack. Now, I put some scale in there, right? It doesn't come without thinking about it. The difference between a 30 amp connector, a 60 amp connector, a 100 amp connector, and 8 of them in a rack, go look at the busway tables over there from Starline and Delta and a few others and where do I put all these? You got to think about it up front. So at the server level, I've talked about some of my other partners, so I wanted to grab a slide from Lenovo. And so they're showing a bunch of the components inside the GPU tray, showing how 50-volt power gets distributed, showing how there's leak detection everywhere, where water covers a bunch of components. And we believe that when you look at the OCP OpenRack ORV3 at 50 volts, that we can easily get to 300 amps into the server using 25 liters per minute of hot water, that we can get to 15 kilowatts a U. So without even breaking a sweat, no pun intended, is that we believe that the technology even today allows a 600 kilowatt rack. But you got to model it. So I'm sure many of you have seen 3D modeling of your own data centers. So here's a 6900 GPU hall. Got 2 water temperatures, fan walls of the perimeter, 4 to make 3 power buses. You got to make sure that it all fits, that you've got energy control valves on the water. And we do this. Actually, talk to your NVIDIA sales rep, and we have our Omniverse. It's a big part of the video stuff that we do. So we model, ETAP, modeling from electrical. We can model the water temperature, the air temperature. You can put your Google glasses on or your Apple Vision, and you can study it all in real time. But you got to model it. You got to make sure you got every breaker you can reach. You got every patch panel you can reach. So it is a little different, but is it really that different? So I'm going to wrap up here in the next about 10 minutes and say, how is it different? What do you folks think about how different it is? Well, it just so happens that in Houston, Texas, in my backyard, you guys know that's not really Houston, right? In Houston, Texas, in my backyard, there's a data center being built for me. And it doesn't look all that different than a data center built 10 years ago, 15 years ago. They built it in a modular fashion. And if we look at a print from the data center, the front yard is a bunch of generators, 10 generators in a tiering fashion. You've got UPSs in it. You've got perimeter CRAs, and you've got a white space. This is a true data center print because they even show where the smoking area needs to be. For the Gen Zers, that's the smoking, not vaping, smoking area. And so as we go down into it, it's 2 stories, 2 halls of IT at 8 megawatts a hall. All of the cooling is on the roof. But you know what? This could be any colo. The difference between this picture and a colo built 10 years ago is it would have been a 2 megawatt A and B hall 10 years ago. Then it's a 4 megawatt, then it's a 6 megawatt. So in the current technology, depending on your favorite colo, this is what a 16 megawatt building block, 8 megawatt over 8 megawatt looks like. And the kit inside is not all that different. Lots of air handlers filling the perimeter. Still A and B power, 22 kilowatts a rack, and not protecting the innocent here. They're building a brand new data center, and until somebody tells them differently, they're going to keep building it this way because they keep selling it. They're going to build gigawatts of data centers just like this. But what happens then if that thing I talked about, power increases? Well, we already know it's increasing when we went from H100 air-cooled to what a Dell, HPE, Lenovo, Supermicro did to make it more dense. And it doesn't take rocket science. to go, okay, I lose 2/3 of the equipment. The outside didn't change. It really wasn't any different. Am I going to really save something by compressing it down? And so let me give you a real life example of this. In this hall, not this one, but one that was just like this, we could put 2 EOS supercomputers. EOS was when we did liquid cooling on the H100. It's still today the number 10 supercomputer in the world. So we could put 2 number 10 supercomputers. Now, this was a couple years ago, so we didn't go 8 chassis a rack with liquid cooling. We kind of kept it a little bit more spacious because we wanted to make sure that we got full performance out of it. But the data center could take it. We could go to any colo at the time and say, hey, gives us freedom to go to any colo and say, can you put it in here? So the future. I showed you the picture of Vinson standing in front of it. So we've got full Omniverse. This is digital SketchUp. Dennis is probably in the room. Talk to Dennis if you want to learn how to model everything. Water feeds. This is showing water overhead, power busways. But this is a repeatable building block that just scales. So basically, just to make it easy, that there are 8 1 megawatt, like I showed in the 1.1 megawatt, just rounding here in the room. But what if that crazy future happens and power doubles? Did you do anything different? Yeah, the 1 megawatt chunk got a little tighter, but did you really change the room? And again, as I start to wind down here, what does that mean to the outside? I still have each one of those rooms are 8 megawatt rooms, room over room. So it's a 48 megawatt data center. In this picture, I kind of cheated a little bit. I took the A and B networking equipment and storage equipment and I moved it someplace else. And I said, just for argument's sake, I went and made that those 8 1 megawatt groupings smaller just to show what's possible. So again, that's a tripling or quadrupling from today's density, and I didn't change the data center. But nobody knows what's going to happen in the future, so let's go on this journey together. I want to double it again. Now, because remember I told you it was 2 floors of data centers? I think it's outpatient surgery to take the power from the 2nd floor and run it to the 1st floor. I didn't fundamentally change the data center. Yeah, the green blocks around it might be different RPPs. They might be different UPS technology. They might be 1,000 volts DC. It doesn't really matter. It could be immersion tanks. None of it matters. The point is the data center didn't change as we quadrupled and octupled. It was still the same data center. But let's keep going. So again, we don't want you to be afraid of the future. 32 1 megawatt things in a common space. Now this is different. I did 2 things in this picture. Number 1, I assumed that my partners at VoltaGrid and R Power and Schneider and Emerson and Liebherr and everybody, they're going to improve and make 3-story or 4-story generators. Maybe they're Yuval's hydrogen fuel cells, or maybe they're Bloom Energy cells. But the point is that I suspended disbelief for a second, and I could put 32 megawatts of resilient power in the foreground. I needed a lot more cooling, so I had to call my neighbor and say, hey, can I rent your back acre to put dry coolers on? But the reality is, that's dumb. I should not have to do that. I should have to take every bit of water there, I want to send to the local municipality for heat reuse. I want to send it to the local coffee dryer. I want to send it to the swimming pool. I want to send it to the apartment building. I want to do desalinization for it. I want to heat up greenhouses with it. Google's got a patent where they're actually taking waste heat to do carbon sequestration. So I don't want to waste money on the heat that I've already got. So really, I don't want to even put that in there. Now, you can see this is not the same data center. It looked close. So I said, okay, let me build a custom data center just for AI. So I put all these things together. I have a big tight network spine, 128 megawatts, and I'm not kidding you. When I made this picture, nobody saw the overhead view of Memphis with a bunch of stuff around it, or potentially a bunch of stuff around it at 128 megawatts. But I mean, that's literally what it would take and the stuff around it, even if we went, what was that, 32 times the density we are today. So that's a custom data center. But the education, the feedback I want to hear from you when it's over is, why is it any different than this? These 8 megawatt halls, So what that some of the volume of the data center, white space, the acreage, only 20% of it was the volume anyway. And I think somebody accused me of picking a local data center in my backyard that was great for this analysis. Well, it turns out in Houston, there's a data center in my front yard as well. And what's eerie about that data center is within a few square millimeters, it's almost the exact same footprint for 16 megawatts. And it's a standard colo that everybody would know. Both of them are standard colos that everybody would know. The power technology is a little different. The cooling technology is a little different. Those are cooling towers on the roof. But inside, when you peel back the roof, you got 2 stories of extreme low density IT at 15 kilowatts a rack. And then I would put in, and I am putting into that data center, the green blocks, 8 of them, or 16 of them on the first floor, 16 of them on the second floor. And I didn't really have to change the data center. So finally, one final comment here on data center design. Even though we can use 45-degree water to the chips, we don't know what's going to happen in physics. I believe that there might be a day where we need to make colder water, but that's not today. That's not 2028. That's not 2030. So it's not that hard to put 100% of the pad, 100% of the piping, 100% of the power for the day when you need colder water, right? You just have the same cooling towers. It's the same heat rejection, right? Heat rejection takes the same amount of space. And so I would argue, pass the bill down the road. Plan for putting in colder water, but don't throw your money into that today. Save the CapEx, save the OpEx, save the scarce power and buy more GPUs. Don't put it into the cooling there. And someday, if we do need to make it cooler, or you have to buy your chips from somebody whose chips can't run with that, because I know you can't buy them all from us. So finally, data center in my front yard, data center in my backyard, how different has it been than data centers in the last 15 years? And the thing is, you just have to prepare for it. So last thing I'll leave you with, remember I said hot chips? We came out with some stuff and some cool images. So there's actually looking down at the Grace Blackwell with the copper, with the water, with the power. There's the NVLink switch. Matter of fact, there's a data center that actually didn't have liquid. So they had a liquid to air sidecar enabled to do that. So hopefully you've learned it a little bit, you inspired you a little bit, you see that this is something you can all participate in this. You don't have to be afraid. Where's Bill Clayman? You just get fearless or brave. That's the word. Got to be brave. It's cowboy hat. Got to be brave. We're here to help you. And I don't know if I got any questions coming in. How'd I do? I consider today a success because I already stayed up more times than I did on the wake surfing yesterday. So, it was better than I did yesterday for those in the boat. Questions? I know Kirk's probably dying to ask me something too. It was so self-explanatory. You all get it. You're all going to go back, tell your CEOs to give you more money, hire more people. You can all participate. Yeah, have I tested submersion tanks? Matter of fact, I owned a submersion tank at HP, the very first Green Revolution tank in 2010. And it's interesting technology. Heck, at Compaq, I put servers in cooking oil because I was a little bit younger then in 1997. And it's an interesting technology. I look at what we're doing with cold plates and rear door heat exchangers and the complexity of the IT and the signal integrity is that, when I look at it, it's like, there are people who want to do submersion. A lot of companies want to go that route. You just got to get the server vendor that you're buying the server from to be able to tell you it can be done. Treatment necessary of the water after it's used for cooling. Well, the water never goes away. It's just the loop. Right? We're not talking about evaporative cooling. And so the water inside the chip is propylene glycol, 25% RecoChem OAT25, the magic recipe for water, got azoles to protect the yellow metals and a few things to prevent biogrowth, but that is the fluid loop inside of everything. I'm just reading the next one. Why are not going underground with data centers? You looked at the footprint, and by the way, when I left HP, I had an underground data center. What did it change, right? I mean, every volt amp that goes into a server's never had a shaft. A server is just a heater. And so I've got to remove every volt amp coming in or the server doesn't run. So putting it underground doesn't really solve anything. I still have to take every volt amp and I have to cool it down to keep the server running. So underground doesn't really change it. Single phase cold plate. People that I work with in this room, we've been looking at the technology, and as we work with ASHRAE and OCP, I'm gonna put a little plug in for OCP in ASHRAE, we're looking to increase the velocity limits that are based on, back when you were an engineer, designing B-52s, right? You can increase the velocity in pipes. You can increase the flow rate. So we believe that we can extend single phase cooling for quite a long time. Now that we're closer, well, we're already, I hope maybe somebody asked this question early, whether or not we're a 500 kilowatt rack. I would argue that the Cray EX systems that you see, that running at full performance could have already been there. Why did Elon? Elon is about fast. Everything he does is fast. Other than that, I don't get to talk to Elon about that. Okay, difference between a 20 kilowatt rack and a 100 kilowatt rack. Again, density for density's sake is dumb. We're doing it because it gets more performance per dollar, performance per watt, and the data center doesn't have to change. We do have a lot of data centers in cold spaces, as someone asked. It's more energy efficient. A lot of them have hydroelectric power or geothermal in a lot of those cold places. But we're talking about, AI is going everywhere. AI needs to be close to some people for inference. So you can't afford the latency of putting them all in this place that has great cooling. I mean, Abu Dhabi and Malaysia, right? Data centers go there. That's not cold. Overhead underfloor, it's a preference. What we like about underfloor is that a lot of times, because you got a loading dock that pulls up here, you're already got one height, so by definition, you probably have an underfloor anyway. And if water's the utility underfloor, it's a little bit easier to service. But a lot of people put data centers on just concrete floors in a warehouse, and so you can run water overhead. I think we understand how to build good, you folks understand how to build good high pressure piping, test it, commission it, nice fittings in it, good chemistry in it, leak detection, leak pans in it. So I don't think we're afraid of water overhead. Is ASIC a consideration in your outlook internal terms and competition? It's hard to know what it is that is driving other people to ask for a much colder temperature. I'm very close to what we're doing at NVIDIA, and I know what temperatures we can run at. I can only assume that following Moore's law, following the scaling, is that in order to get the chip to perform at higher frequency, they have to run it colder. We found other ways to do that. As a service, why doesn't NVIDIA offer GPU service thing? We have partners. Jensen loves to talk about our partners, and you saw them out there. Linda, I mentioned quite a few of them. And so we build our own DGX branded version of it because it's got our software stack on it. It's a full turnkey solution from us. And we run the DGX stuff inside a Google Cloud or inside an OCI Cloud or someplace else. So we do offer it because we have to do it ourselves to validate it. But we think that we do the design work, but we enable everybody to play because the whole world needs everybody to play, right? There's just not enough of us doing it. Leaks in the water cooling versus air issues. I mean, if you have water, you probably have dealt with a leak in the past. And as long as you know your mitigation strategies, your downtime events, being able to understand what that means to your server uptime, people are using it. And you can't do it with air, right? It's just I have 50 US patents. Many of them are on air cooling fan technologies. And you can't push fans any faster than I pushed them. It was a jet engine, if you guys have seen it, right? And I mean, it's just, there are limits of the M.dot CP delta T. You just can't get the chips cool enough. Percent heat rejected by water, great comment. We put as much as needed, as little as possible, that's a Jensen phrase, on our cold plates. So we don't cold plate everything. But we believe that if we can get to, in the GPU rack, 80% of the heat into the water, and then the support racks are low density today, so they don't need it. But in the future, I expect support racks will go up. So I think we're probably, as an industry, 60-40, 70-30, trending to 80-20. And as the power goes up in the data center, I expect that there will be some fixed limit of air movement, right? I'm saying you can do about 2.5 megawatts of air cooling in those rooms. Maybe 3.5, and you push it. So as we have higher and higher density kit, the volume of air, the percent removed by air is only so much. So it's like the term relative and absolute humidity, right? The percentage of it doesn't change, but the relative nature of it does once we reach the limits of air cooling. All right, what else? Any other questions that were done, that we skipped over? Blake, yeah, Blake.
How much does a standard Blackwell rack weigh when it's full of liquid?
Okay, so we were asked how much does a standard GB200 NVL72, when I get to the right words, rack weigh when it's full of liquid. All things included, it's slightly less than about 3,400 pounds. So from a floor tile perspective, we believe your well-designed data centers can do it. When you look at the pictures of the Cray system, as we go up in power, I think the rack gets spread out a little bit. So from a weighting perspective, some floor people are in here. If you got 5,000 pound rated, for a single rack, as it spreads out across racks, we're very cautious to make sure we're not doing something that eliminates truck transports, that eliminates, elevators in Europe. So weight is very important to us. And so you got to get all that copper and water in there, but it's not any more dense than the stuff that I did at HB and Cray 10 years ago. Questions in the back?
Yeah, what impact are you seeing on the commissioning process?
What impact are we seeing in the commissioning process? And the answer is, who stopped doing commissioning? That's just crazy, right? You got to commission it. You need to make sure your liquid cooling is fully commissioned before we roll in, this X $1 million rack, and you put water that has only been filtered at 50 parts per million, and you foul up your whole system. So you definitely need to make sure that you commission it, and when you're done, you take those filters out and you put a different set of filters in. Commissioning is so important. And I see a lot of people, a lot of our partners are doing in-rack CDUs as opposed to big CDUs because they believe that it helps the commissioning story. Is that you can commission the data center as a water feed, and then your CDU is there instead of trying to get enough load to commission big CDUs. NVIDIA, we got awesome server emulators to commission a full data center. So if you want to commission it, come talk to me and we'll figure out how to scale so that everybody can commission with our true performance per watt, performance per dollar emulators. Question?
Yes, are you seeing as it relates to customers buying GPUs and then their usage of the GPUs, have you seen their usage of GPUs exceed expectations?
So he asked, as people buy GPUs, are there like CPUs where they buy them and they don't use them? Are they fully utilizing? Yes, and it's pretty scary.
Are they using that greater
Yeah. So because they are so efficient and they're doing the work, and we're just in the infancy of coders, the Llama model versus the XGrok model versus the Chat GPT, everyone tries to figure out how to squeeze every last bit of it. And it's not just the 8 GPUs here. It's not just the 72. I mean, literally, we have people, 10,000 GPUs, that are milliseconds at peak and milliseconds at nothing. And it does that all the time. So the generators, the UPSs, the facilities, many of you in the room are having these conversations with us, and you got to make sure that you understand this is different than CPU computing in order to get in order to trap this inefficiency of computation inflation. Power is just different.
Is power the biggest limit for everything you're doing today?
I don't know that we have any one limit right now. I think because we're pushing it on every single generation. And so there are times where it's supply chains, or sometimes it's power, or sometimes it's cooling equipment. There's a lot of capital being spent by the investment banks to make sure we don't have limits. There's a lot that we're doing, investing to make sure we don't have limits. I don't think we have limits today. I always say, just get out of the inefficient CPUs, and there's a lot of power left over. Of course, then we'll run into Javon's paradoxes. We've already squeezed every bit of inefficient CPU out. Then, what happens next? Any questions from the mez? Do I see a hand? Yes.
Has there been any effect on the utilities, especially with these large supercomputers, where you're talking about 400K racks?
Yeah, so that's Bert, right? Yes, Bert from Amazon back there. Anything affecting utilities. And as people are in the last 2 years are building these larger and larger models and seeing this DIDT, in this shift, the first thing that happens is the UPS will see it, and so they got to make sure that their software and the quality of the UPS can deal with it. The next thing would be during a generator start, and then finally would be, can the utility deal with it in the utilities usually RMS over a few seconds. Hey, utilities are used to dealing with frac machines and rock crushers, so utilities in general, Bert, we've seen are less freaked out about the DIDT, but that doesn't mean we don't have to keep looking at it. So we just hired Sean Harris, came over from Microsoft, and he and I talk every day about DIDT capacitance in the system so that we can continue to build the highest performance per dollar, performance per watt systems to keep up with that white line on the data center demand. How we doing? Oh, I think we're done. Thank you very much.
Wade Vinson, everybody. Great stuff, great information, and really, y'all killed it with the questions. Those QR codes can be a great way for us to keep communicating with our speakers.